Good morning, calculators.
Hey, good morning.
Outstanding. Another day is upon us. Sharing the screen. And off we go. Seems like the kind of day we should write on graph paper. So, where are we? And I guess before I start, I always would prefer you just interrupting me, but I happen to suddenly remember that I did say if you stay through the 12.1 assignment and have any questions, please ask them. So now's your chance before we look at something else. So 12.2, we're talking about polar equations, and they are a rather fascinating little creature. Again, I'd be disappointed to know, as the department chair in math, if your Math 112 teacher, your pre-calculus teacher, depending on where and when you had trig, didn't have time or didn't make time, I should say, to show you polar equations, because they are a rather lovely little business. And they're super simple. But it has to do with this. You already understand it, even if they didn't teach that to you, just because you took trig. And so let me remind you of that fact. And this opens up a kind of a crazy world. And parametric equations did that too. And I hope you leave that thinking of that sort of third parameter of time being put in there, which creates directional graphs. And they're the same. It's no different than an y equals x or a rectangular graph. It's just that now they have direction and time associated with them. And so we can still do calculus to all of the equations that we get as a result. And hopefully that is sinking in upon you as you study this stuff. But now we're going to look at another class of equations that also is just another way of saying the same thing. Don't make this too complicated. But it has to do with this, and this is why I say you already understand this. You don't need any formulas for this. If I said to you, my friends, let us graph the point 5, 3, you know, of course, that this is rectangular coordinates, or sometimes called Cartesian coordinates. And so it's a way of locating a point in two-dimensional space. If you take Calc 4 this summer, you will jump up a dimension and go into three-dimensional space, and your mind will be blown. I hope you need that so that you're sort of forced to take it. It's unbelievably cool. And we'll do calculus in 3 dimensions. But you can locate that point by saying, I'm going to go over 5 and up 3. And so that's how we get there. We get there rectangularly. We turn to 90 degrees as we went over 5 and up 3. That's what's called rectangular coordinates. But you can also get there through, well, what you know about right triangles. And this is the way airplanes would do it, or ships. You just go straight to your destination. You don't travel, 5 blocks to the right and 3 blocks up. You do that in a taxi. But in an airplane, you would actually just turn however many degrees this is right here. And you would take off whatever this distance is right here. I'm going to call it R for radius, because this is kind of where a circle comes in. And that's what you did in trig. And so it's pretty easy to figure those two things out. If I said, hey, the tangent of theta is opposite over adjacent. And because we are in advanced, I'll just leave that angle in radians. Am I in radian mode? I am not, since I'm teaching engineering. So if I say the inverse tangent of 3 divided by 5, I get the angle 0.54. So theta, hence theta is approximately 0.54 radians. And of course, I could do Pythagorean theorem on 3 and 5 to get r. So if I take 3 squared and 5 and square them and add them together, I get the square root of 25 and 9, which is 34. So r is the square root of 34, which, thanks to the last chapter, we have a calculator because we have a power series expansion now for what the square root of x looks like. Keep in mind, I've mentioned this a little bit, but historically, nobody knew what the square root of 34 was. They just knew it was a number that when squared is 34. They knew the square root of 36 was 6, so they knew the answer to this was a little less than 5. But this was a source of great consternation to ancient people because they didn't even have a number system that would even allow them to come up with a number for this, because all their numbers were fractions. And this answer is not a fraction. It's not ratioable. It's not rational, we say in mathematics. And so the very fact that we blithely just punch calculator buttons and say, oh, that's about 5.831. I hope now that you have an incredible sense of mystery as to how amazing it is that we have a machine that will produce an approximation to that. That is unbelievable. And so does it make sense if you're in a ship, you could say, I'm going to turn 0.54 radians and then sail 5.83 miles, and then I'll get there at the same destination. And notice, of course, that's why ships do it, because it takes 5 miles and 3 miles, 8 miles of sailing to get to that point. Well, that'd be dumb when you can just go 5.8 miles and go straight there. That's all polar coordinates are. So how do we list the coordinates of that point? We used to say that the coordinates of that point were 5, 3, and we call that an ordered pair because 5, 3 is not the same as 3, 5, and it's a pair of numbers. It takes 2 numbers to describe that point. It'll take 3 numbers to describe that point as soon as we go to 3 dimensions in Calc 4, but that is also equal to what in the world of polar you say is the square root of 34 and 0.54. In other words, that is the angle and that is the radius. Now that's a little, I said that backwards. That is the angle and that is the radius. That's always struck me as backwards because I guess it's just because of the simplicity with which I think about this. In other words, if I'm sitting right here, my first thought would be, okay, well, I'm aiming to north, and first thing I would do is kind of turn 0.54 radians, and then secondly, I would move a distance. And so these always feel backwards to me. I have to concentrate to get that order correct. So that's an ordered pair as well. But what you've just learned is this is the rectangular version, and this is the polar version. It's 2 ways of saying the same thing. It's just that simple. And so, well, who cares? Like, what good is that? Well, it turns out just to simplify things immensely, well, certain graphs are immensely simplified. Let's just make a note of something, though. Given that this was our x and this was our y, did you notice to get r then, we basically said r can be found by taking the square root of x squared plus y squared? Like that would be a formula that you would see in this section that I hope you don't need. And then we took the inverse tangent to get the angle. We took the inverse tangent. So theta was found by taking the inverse tangent of, and let's see which was which. It was 3/5. And you should be able to see from the picture, that's y over x. And so you would see these formulas as to how to convert kind of from one world to the other. And we did that in the last section. We converted from rectangular into parametric and vice versa. We did that a little bit. And that's kind of true in this world as well. And so that's kind of interesting. Well, let me show you an example of a place this is so powerful. Perhaps you remember that the equation of a circle in rectangular is x squared plus y squared, x squared and y squared. And I didn't say x minus 2 squared. That allows it to shift left and right and so forth. And then over here is just the radius squared. So let's say I made that 25 or something like that. That's a circle centered at 0, 0 with a radius of 5. And you may notice the equation for that circle, if you weren't taught this before, actually just entirely comes from Pythagorean theorem. In other words, if I'm over here with a circle of radius 5, whoa, isn't that interesting? I didn't make a circle at all. If I'm over here with a circle of radius 5, isn't every single point on that circle, since this is always 5, isn't this the x and this the y? And so wouldn't x squared plus y squared equal 5 squared? Because of Pythagorean theorem, the equation of a circle is the Pythagorean theorem. That's just kind of an interesting observation. Well, let's convert that to polar. Well, notice right here, this is one of the best equations in polar that there is. Notice right here, if I just make a slight modification and I square both sides of that, I just get this. And that's what circles are for. In other words, you could just replace x squared plus y squared with r squared. So this is a rectangular version of a circle. This is the polar version. Notice how simple that is. And if you think about it, notice that actually makes perfect sense. We need a bunch of points graphed. In the rectangular version, it was like, I need a bunch of points graphed where x squared plus y squared is always 25. You find any 2 points, any x and any y that make that true, boom, graph the point. It'll make a circle. What do you do down here? Well, just make sure the radius is 5. What's the angle? You didn't tell us anything about the angle. Well, the angle's everything. Make the angle anything you want as long as the distance away is 5. Imagine yourself going out 5, out 5, out 5. Turn an angle of 80 degrees, go out 5. Turn an angle of 90 degrees, go out 5. Turn an angle of 300 degrees, go out 5. Yeah, that'd make a circle, wouldn't it? And so notice in polar, your graphing calculator, and I'll go to your graphing calculator some too, also has a polar mode. We switched it into parametric mode last time, and you can also switch it into polar mode. Desmos, you don't have to switch it, it just knows. So if I go in here and say x squared plus y squared equals 25, you should not be surprised to see a circle of radius 5 from your algebra knowledge. But I can just go in here and say r equals 5 and accomplish the exact same thing. So it knows polar, it knows that. It doesn't see r as like another one of the letters. If that's a special one, just like t was. That's a special one. So it's the exact same circle. So that's kind of cool. So polar equations don't have x's and y's, they have r's and thetas in them. That's what they've got. And so, well, let's just play, since we're here for a second, let's just play around with this a little bit.
How would you move it like to the right, like +2 on the other one? How would you do that with r?
That's a wonderful question. Watch what happens if I'll let you kind of discover that as I just kind of play here for a second. Like what if that, like I want to get theta involved too. And don't we have that for x's and y's? Like if I just say x equals 2, let's think about that for a second. If I say x equals 2, what's the graph? Well, it's like, well, what's y? There's no y in my equation. Again, some people have trouble with that because they're just trying to memorize, and you might be doing this in your head right now too. Let's see, was that a vertical line or a horizontal line? It's like a flip of a coin. It's 50-50. No, if I say x equals 2, you should just say, just make sure all your points have an x coordinate of 2, right? So if x is 2, yeah, x is 2, x is 2, x is 2, x is 2. Oh, look at that. It makes a vertical line. So there's the equation. As long as x is 2, then the other point, the y can be anything you want. In other words, that's why y wasn't stated. Y is everything. Well, it's the same with r equals 5. What's theta? Everything. And so no different. However, the more interesting equations in lines have x's and y's, right? And so you might say not x equals 2, but x equals 2 plus 3y or something like that. And then you're going to get in a line that's a little more interesting. And the same thing is true with polar. So my first equation was just r equals 5, if you will, the simplest and most useful version of a circle possible. And you might appreciate that if I had to do a bunch of math to a circle, using an equation called r equals 5 might be a lot easier mathematically than it would be to do it to x squared plus y squared equals 25. And so that's one of the reasons for the creation of this, if you will, just different coordinate system. But let's go in here and just throw some thetas in here. Like what would happen if I threw, well, just a theta in there? Let's see. I don't even know if that's one of the buttons. I think I just have to type it, but let me just check because I don't remember. Mistake. How do I get my I'm very good at this app. How do I get that back? I lost my, oh, I know how. Let's see, is there a theta in here? What if I hit this? Oh, there's one right there. Well, that's interesting. That's kind of fun. Why would it look like that? Kind of creates a spiral. Think about ordered pairs. Why would it look like that? It might be easier for you to think of this in degrees for just a minute. So I'm going to switch to degrees. And while we're at it, they even have a thing in here called polar graph paper. So let's switch to that. And maybe I'll change that from a 5 back to a 1, just so that it doesn't grow quite so fast. But think about this. If you pick 30 degrees, if you pick 30 degrees for theta, then notice 30 times 1 is 30. Well, then that means r is 30. Does that make sense? So if you pick 30 degrees, then your radius is 30. Oh, okay. Well, that makes sense then. Because look, can you see the point 30 degrees and then a radius of 30? Can you see that point there? Actually, I'm not sure if it's going to do this right. How does it know that I'm in polar if I just type points? I actually don't know. Let's see. So we have to say 30 comma 30. Come on, I hit 0. That was not my fault. Notice it's not working. It's graphing that as a rectangular point. I actually don't know. Is there some way to make it graph that as a polar point? It didn't do that. So
maybe you could add degrees on your theta.
Yeah, maybe add a degree symbol or something. That's an interesting, it seems like it would be possible, doesn't it, somehow to do that. I don't know if there is a degree symbol on my screen here, so just quickly looking. I don't see one. I'll have to think about that. But the point is, do you see the point 30, 30 where the radius is actually 30? And so, oh, I see why this is growing like it is, because if the angle is 40, then the radius will be 40. If the angle's 80, the radius will be 80. So as I turn around, the radius just gets longer and longer and longer. And so part of this is just fun. Like you get interesting graphs. A spiral is not something you can make in y equals x. And you might appreciate that spirals are how sunflowers grow and so forth. And so these actually model things, or shells at the ocean and so forth. There's things that are modeled by this. And so this opens up a world of graphs that we didn't have before, just like parametric. Especially parametric opened up the way for things to fly through the air and for us to kind of know where they are and how fast they're going, what's going on. And so polar opens up a world too. What if it wasn't just 1, but let's put our 5 back in, but let's say, I don't know, let's try cosine. What happens if I say the cosine of theta? There's no graph. Why is there no graph?
Zoom in.
Yeah, you see it down there? Remember, cosine of theta only gives answers that are 1 and smaller. Therefore, the biggest radius I'm ever going to get here is 5. Well, look how large my graph is. And so there it is. Notice you now have a hint. Was that Connor that asked that? A hint of, it's like, isn't that still a circle of radius 5? But notice it's been moved right, I guess 2.5. So that's kind of interesting. I'm going to go back to regular graph paper. So if I put a 6 there, would you agree that's still the circle x squared plus y squared equals, well, now 36, except for it's been slid right 3. So apparently then that's the same equation. I'm going to write this down. Apparently r equals 6 cosine of theta, since it basically was a circle of radius 6 that slid right 3, is the same thing as do you agree with that? If I replace x with x minus 3, doesn't that slide something right 3? So apparently those are the same thing. Those are the same exact circle. I wonder if there's some way we could kind of, show that or prove that, or, convert. Is there some way we could convert that? Well, why don't we stop and play there for just a second, since I asked the question. Anybody have any ideas? Apparently those are the same. How could I either go from the polar version and get it to look just like this, or perhaps go from the rectangular version and get it to look like that? I don't really know which one to do, but how could I do that? Well, think about the connection that you have here. This was our connection. This is x, this is y, this is r, this is theta. Don't we have relationships for those things? Like, for instance, if I was going in this direction, I'm going to follow up with that one. Couldn't I replace r with, well, r would be Pythagorean theorem. Wouldn't r be equal to the square root of x squared plus y squared? So then that top equation would be not r equals 6 cosine of theta, but square root of x squared plus y squared equals 6 cosine of theta. But what's cosine of theta? Isn't cosine of theta adjacent over hypotenuse? So I could say 6 times x over r. So notice I'm getting x's and y's to show up. I'm basically just trying to get rid of r's and thetas and get x's and y's, and I'm succeeding, except for the fact that I still have an r that produced an r. But again, don't I know that r is equal to the square root of x squared plus y squared? So then, cool. Then don't I have the square root of x squared plus y squared on the left and on the right? So if I multiplied it up to this side, then wouldn't be x squared plus y squared equals 6x? You agree with that? Now, right now, that is now a rectangular equation. If I went into Desmos and just graphed that, I would get the same exact circle. So it's rectangular now. Why is it rectangular? Because it only has x's and y's. Now, this isn't the right form of rectangular. Just like, for instance, I'm going to erase this, but if I told you 4x minus 2y equals 7, you would say, hey, that's a line, because it's x and y, not x squared and y squared. It's just a line, but you don't know what the slope is. It's not in the right form. Well, our circle here is also recognizable as a circle because there's an x squared and a y squared, but it's not in the right form. And so could you get it in the right form? Well, you would have to subtract 6x over to this side. And now you'd have equals 0 over here. But to get this to look correct, we need this not to have an x term in it, but to have something that's a perfect square. Well, to get it to be a perfect square, I would have to add 9 to this side. Is something wrong here? suddenly worried that something is wrong.
Are you forgetting about the sliding to the right 3?
I shouldn't have to do that. It should take care of itself. Oh, I know what's wrong. I'll go ahead and let it happen, and then we'll talk about it. Actually, maybe I'll fix it right now real quick. So I put that there as, what's the radius of the circle that I just graphed? This is the mistake I made. Notice I said, okay, the equation is r equals 6 cosine of theta. And we said, oh, cool, look at that. There it is. But what's the radius of that circle? It's not 6. That was what was wrong with what I wrote.
3.
It's 3, isn't it? So if that's true, then, and I won't fix this completely, that should not have been 6 squared. It should have been 3 squared. Does that make sense? So to get this to look like this, then wouldn't I have to add 9 to this side so that that x minus 6x plus 9 is a perfect square, which can now be written in this form? And if I add 9 to that side, I've got to add 9 to this side. Notice now it's in the right form. These equations are the same. They're equal. It's just that the second one is in the right form for a circle. Now you can say, yeah, it's still x squared and y squared, but I know it's a circle of radius 3. Notice up here, I did not know the radius was equal to 3. There's no way I could know that, but it's still radius 3. So I was done. It's just that it wasn't in a form where I could kind of easily graph it. So do you see they really are the same? I mean, that's kind of cool. Just to give you a second to think about that, let's go over here and we'll graph the first one. I had x squared plus y squared equals 6x. Look at that, same exact thing. So I was done right there. If somebody said convert that graph r equals 6 cosine of theta to rectangular, your goal is just to keep getting rid of r's and thetas until you just have x's and y's. Once you've done that, mission accomplished. But if you are good at circles, you would say, okay, I know that's a circle, but I don't know where it is. I don't know, is it moved somewhere? And I don't know what its radius is. And so if you complete the square and you know how to get it in the right form, that second form was a lot better. And I won't take the time to graph that, but it's the same graph. And so what I'm saying is, do you agree that that's like, this is nothing new? Like I already can graph a circle. I can already graph this. I don't need r equals 6 cosine of theta. However, r equals 6 cosine of theta is a nicer version of a circle. And if we are going to have to do advanced math to it, maybe we'd want to do that with 6 cosine of theta instead of with the uglier version of a parabola looking, it's squared, right? It's going to have quadratic formula associated with it. Nothing is squared up there for that other one, r and theta, they're not squared. And so maybe that's just another way of saying the same thing, just like the 0.35. And the way to say it is 0.54, whatever it was, 0.54 and square root of 34. It's like no different. It's just two ways of saying the same thing. Don't make this complicated. It's not complicated. Let's play around a little more. Like I just messed around with that, but let's really get kind of screw off here a little bit. What if I squared? I have no idea. Like I have not prepared this. This is just part of the fun. I wouldn't want to prepare this. So, whoa, what in the world is that? I don't even know what I'm looking at. Do you? It's like so complicated. It doesn't even seem to, I don't even know what I'm looking at. Oops, I just screwed up go back to square. I don't even know what I'm looking at there. That's totally confusing to me. I wonder if I made that a 1. That didn't really help. Let's see. What if I had, I don't know, like 2 cosine of theta, but then what if I added a sign to it, like plus 3, say sine of theta? Well, even where I stopped right there, that's kind of cool, isn't it? What? You just added 3 to it? Isn't that strange? A second ago, before I added 3, it was just a circle of radius 1. I'm basically saying, no, I'd like the radius to be 3 bigger than that. And then it produced that. Isn't that rather strange?
That's weird.
So I find myself thinking, what? Like I want to make my own ordered pairs. You know what I'm saying? I want to pick 10 degrees and 20 degrees and 30 degrees and 40 degrees and take 2 multiplied by the cosine of that and add 3 to it. And so how come it isn't just a circle that's got a radius that's 3 bigger than it was before? Does that bother you? Because that was my first thought. Like if I just add 3 to it, won't the radius just be 3 bigger? I'll leave you to ponder on that. So then I find myself wanting to play with that number. In other words, instead of putting a 3 there, I'm going to put a C there so that I can slide it. So, ooh, that's pretty fun. So notice it. So it comes in, it kind of looks like a heart now. And then it sort of folds in on itself. And wow, I mean, that's just really cool. And then it's like the exact same, oh, C is 0, so it's a circle. And then it kind of heads off in the other direction. So, you know, what a crazy graph. So that's just kind of interesting. Again, if you want to just look at this as art, that's a very artistically beautiful graph. And that's possible in polar, and it would not be possible in rectangular. Do you understand that? And then I wonder what that 2 is doing over there. So the beautiful thing about Desmos, I'm going to say D, and then it says make a slider for that. So then I slide that around, and it's like, oh, okay, so it's kind of like D changes the size. And this class of equations kind of looks like that. So D controls the size of it, and C kind of controls the loop-de-loop section of it. I mean, that's kind of fun, right? So that's kind of cool. And it turns out this is actually so cool that it's been given a name. This is cool enough that just like we said, hey, that's a parabola in rectangular, like that's a cool graph. It models how things fly through space. It makes satellite dishes in our house that send and receive signals. And so that's a cool graph. We're actually using it for something. So let's give it a name. Well, this one's given a name too. It's called a cardoid or a limicon. You don't need to know that. But this is one of the kind of the classics. And I don't know if that's just because it's beautiful or if it has some application. I've never looked into the history of that. Cardiology is heart. And so cardoid is kind of heart shaped. And you may notice that if these are the same 5.4, you see how when that became 5.4, they're identical. Do you see how that little loop to loop went away? And anything past that. So it actually comes to a point, an exact point, if they're perfectly equal. So technically that's cardioid. And so maybe that's because it looks like a heart. Not sure. It's kind of like a heart. It's a heart on the left side. It just doesn't come to a point on the right side. Out of curiosity, I wonder what happens if I throw sine in there. Since sine and cosine are so similar, what if I throw sine in there? Not surprisingly, it's the same graph. It's just kind of oriented in another direction. Remember how sine and complementary sine and cosine are 90 degrees apart from each other. So this just rotated the same graph 90 degrees. So that's kind of fun. Now that just happened randomly. I was on my way to wondering what happens if I, add cosine to this. So I wonder if I take the cosine of theta. Is that, again, all I'm doing is playing. I don't have any idea where this is going. So that's just a circle. Oh, maybe that's because those two are the same. No, that's just always a circle, but notice it's in kind of a weird location. I wonder what happens if I go in and like double one of those angles though. Whoa, isn't that fun? This doesn't have a name, but doesn't it seem like it kind of should? And again, this is where Desmos is so fun because you can kind of play around and see what effect these have. Notice it kind of creates a clover right there. When does it create a clover? Well, when the sine term was gone. Do you see how that sine term is gone? That actually does have a name. We'll talk about that in a little bit. but man, this is fun. I mean, this is just cool stuff. So I would call that art. But notice, because we're taking calculus, don't you have all kinds of calculus thoughts here? Like, you know, could you find the slope? Could you find the places where the slopes were vertical or horizontal? Could you find the area inside some of those curves? Like, these are the things calculus people ask, and that's what we'll be tackling tomorrow. It's kind of wading into that a little bit, but it creates a class of equations. This is really neat, really complicated, and so forth. So when D was equal to 0, in other words, that term was gone. So I want to play with this a little bit. Notice C seems to just control the size of it, right? So it's kind of like the radius. That makes sense. If you take R and you multiply it by something, like if I say times 5, then doesn't the radius just get 5 times bigger? So that kind of makes sense. But it's interesting that it produces petals, if you will. This particular one, it also has a name, and it's called a rose. Why would it be called a rose? Well, I chose 2. What if I chose 3? What if I chose 4? So that really doesn't look like a rose. It looks like a flower, but whatever. I wasn't there when they named it. So notice something. Do you see any pattern to the numbers I'm choosing here? So I chose 5. There's what you get. What happens if I choose 6? You seen any patterns? If you're a person that wants, like in a line, we said, hey, that number is the y-intercept. Hey, that number is the slope. What would you say the pattern is here? Let me change this number out here to an 8. Can you see the 8 and the 6 in that picture? It's kind of cool. What do you see?
I saw a pattern with the odd numbers, but not with the even ones.
You saw a pattern with the odd numbers. So if I put a 7 in there, what do you think is going to happen?
It's going to be 7 total leaves, I guess.
Yeah, leaves, petals, whatever. Yeah, you're right. So your hypothesis was correct. There's 7 petals to that. But what if there's 6? So you'd think, oh, there'd be 6, but there's not. How many are there, however?
12, it's 006.
Is it double? So if I put an 8 there, will there be 16? So apparently the answer to that is yes. If you put 4, there'll be double because it's even. There's double the number of petals. And notice 8. Where do you see 8?
In the size.
Yeah. Do you see how that's actually the size? In other words, if you will, the radius of that is 8. The radius of the flower has a radius of 8. So it's kind of like, you know, if this was a thing, if this was, you know, if you thought this was cool or it modeled something, it's kind of neat that you could actually know you could study this and learn and know what the graph was going to look like ahead of time. Isn't that kind of cool? So that's kind of neat. So collectively, those have a name called roses. And it turns out that sine and cosine really don't make any difference. So if I go back in here and make this a sine equation, I didn't notice maybe the petals rotate 90 degrees or they rotate somehow. I think they do, but notice it still creates a flower with a radius of 8 and it still has double the number of petals. And if I put 5 in here, it's going to have 5 petals. And so that's kind of fun. Notice the graph just appears though. Well, wait a second. Did you notice up here that it said from 0 to 180? Let's go back and change this to radians. What if I said I was only going to go to, say, 1 radian? Oh. So actually, if you don't go far enough, then you don't get everything that you want here. So let's see if I go in here and say I'd like to have D. I guess I got to pick another letter. I already used that one. So I'll say B. Doesn't like that. All right. Well, then I'll say B equals 1. equals 1. So notice this is kind of fun. Can you see it actually growing? In other words, the first angle, I'm only saying I'm going to let the angle go up to 0.2 radians. What if I let it go all the way up to, well, what do you notice right there? What angle am I at? What angle am I at when it gets right to 0, do you think? Notice it jumps from 0.6 to 0.7. I don't know, but notice you got to go, let's see how many, isn't that interesting? Notice you're done with the flower after pi. You only need pi radians. We didn't have to go 360 degrees to get this to work. We only had to go to 180 degrees for pi, and it actually completely finished the shape. I wonder if that's true with, notice the answer to that is now no. So it turns out that what was just happening is there actually were 10 petals. It's just that 5 of them were on top of the other 5 when you went 180 degrees. Notice for the sake of, and I didn't know that, embarrassingly. Notice for 6, it takes all 360 degrees or 6.28 radians. It takes all 360 degrees to get the whole flower. So it actually was repeating the previous flower. So in a sense, there were 10 petals. They were just on top of each other, whereas here they're not. That's kind of interesting, isn't it? So this is beautiful. I mean, this is fun. It's amazing, if you will, that somebody said, hey, what if we, named this point another way by its angle and its radius? And then we looked at the type of equations that exist in that world. And suddenly we just have this world of incredible beauty and, such more interesting graphs, if you will. Fascinating. So let's see, now I find myself wanting to go to town. I want to play now. So let's see, R equals, what if I said, I don't know, 4 times the sine of theta. And I don't know, let's multiply it by the cosine of theta. See what happens. Or maybe I should square that. If I squared that, what happens there? So it kind of makes this figure 8 shape. And again, I think, well, what if that wasn't a 4? What if it was something else? And so that's why I want to go back and, call that C, so I can just kind of slide it around a little bit. So that seems to control the size of it, and that's it. But I wonder if I went back in and threw, B in here, what happens then? Well, notice it still kind of creates a flower. But wow, isn't that rather beautiful? Now B was also the number I let this go to. I should probably make this 2 pi just so that it kind of gives us the whole graph. Does that make sense? So I don't really want to mess with that. So now B is actually, so notice that still kind of looks like a flower, if you will. It just sort of grows petals. That's kind of fun. I'm wondering if I went in here and threw cosine, I multiplied it by cosine. That just seems like it'd be fun. So what does that produce? Well, now all of a sudden you get this kind of cool shaped flower. And I wonder if I went in here and, so I multiplied it by something. I wonder if I went in there and let the size of A also change. I wonder what kind of flowers I would get. So C probably makes the size. Yeah, multiplying, so it makes the size. And what does this do? Ooh, that's kind of fun. So it still sort of has a flowerish kind of a design for it. And notice sometimes it lands on itself. But wow, that's kind of fun. Now, the reason sine and cosine make such fun graphs is because remember, sine and cosine just vacillate from 1 to -1. And so it tends to come back on itself. If you have sine and cosine, you get much more interesting graphs, but there's no reason it has to have sine and cosine in it. You just get cool graphs if you do. But it's not like I can't just go in here and say, let's do a parabola of thetas, if you will, and see if that's of any interest. Like what if I said theta squared plus 2 times theta minus 7 or something like that? You know, is that interesting? Notice it kind of just wants to spiral. What you tend to see if you don't have sine and cosine is it just sort of goes and blows up and goes kind of way out in space, if you will. But again, I could go back in front of this and put A, B, and C in here and just kind of mess with those. I wonder if, you know, what am I going to get? What if I don't pick 1, 2, and 7, but what if I pick A, B, and C for these? You know, do I always kind of get the same? Is that fun, if you will? So I'm still getting kind of spiralish sort of graphs. That's kind of interesting, but notice they don't tend to come back on top of themselves. That's the thing that's kind of so fun about getting sine and cosine involved. So all the famous ones, if you will, are based off of sine and cosine. All the ones that are worth naming, if you will. That's just kind of cool. Let's see, let's just play a little bit more. I have one more that has a name that I'm finding myself wanting to show you. I have r squared, and then it's sine of 2 theta. Except for on the other side, I'm suddenly worried that this isn't going to let me graph this. On the other side, that r is not just r, it's r squared. Yeah, it doesn't like that. Let's see. So I guess I could square root both sides, right? I don't know if that'll still work, but notice it says that you can't do that. You have to solve it for r. Isn't the way graphing calculator works? Like you have to solve it for y or you can't do it. Sorry. Desmos, you don't have to do that for x and y, but apparently you do for r. So has to be solved for r. Won't let me do it. Fine. I wonder if I square root the other side then. Annoying. I guess I'm going to have to retype it. Squared sine of 2 times theta, close the parenthesis, get rid of all that other junk. So this one's kind of fun too. Notice the only control I have is over A, but this also has a name. It's called lemniscate, Lemniscates, lemniscate. So it's kind of like a, well, actually, doesn't it look like an infinity sign that's been rotated? And I, of course, wonder what if that wasn't a 2. So with that being a 2, that's the name lemniscate, but what if I made it a 3? Oh, okay, so actually that kind of still just looks like a flower forming again. It's got 3 petals. Apparently this is going to have 4 petals then, right? Yeah, and so that kind of, frankly, it looks like a rose, doesn't it? It's just been rotated, if you will, kind of at a weird angle. Let's see if that's 8. Is there going to be 8 of them? Yep. So actually it just looks like a rose, but it has a special name. I don't know if the graph is the same. Like if I put r squared on the other side, I actually don't know if it'd be the same graph. Remember, you can't take the square root of a negative, but if I square both sides, now all of a sudden the left side, you know, the right side can be negative. And so maybe this is a limitation a little bit on what this graph might really look like. So that's kind of fun. Well, so let me just write this because it just seems like it should be in the note. Here's what I just said. Oh, Rose, I'm having to look at my notes to know this. I don't have this memorized. I'm happy to say I don't think I want to memorize it. If you say A times the sine of n times theta, that's what produces a rose. And this could be a cosine as well. So that was the thing that had flowers and petals on it a minute ago. When n was 3, we had 3 petals. When n was 6, we had double that, 12 petals. And then a lim con. You should just have seen these before. I don't want you to know them. This is nothing I'm going to put on a test, but later on, if you take an advanced math class and the word limicon comes up, at least you can say, well, I've heard of that. A plus or a minus. And we added a number. Remember how that made that heart shape and then it had that curly Q inside it? This is what it looks like. So it could be a plus or a minus. And then lastly, the lemniscate. The one I just showed you, r equals a squared sine of 2 theta. Those are kind of the classic ones. Whatever. When I teach this in Math 112, I say, let's have a contest just see who can come up with the coolest graph. And it's super fun because if you just go into Desmos and start screwing around, and actually I would encourage you to do that right now and tell me, and I'll let you share your screen and show us. But just go in there and screw around, take sine and cube it and add it to tangent and say +7 and screw around. And what I did when I teach Math 112 is have people give them a name. It's like people came up with ones that looked like mosquitoes and they named it a mosquito, and it frankly looked like a mosquito. It was the weirdest thing. But it's kind of fun just to sort of play around and see the graphs. And again, I marvel because this is not something the people that invented this stuff did not have the luxury of playing around with this as much as you and I did. You can appreciate if you don't have a graphing calculator, it's going to take you a year to make one graph, right? And even then, if you don't have a calculator to tell you what the cosine of 1 is, how are you supposed to even do that? So it's like the fact that we can play with this stuff is such a luxury. But let's make sure you can kind of convert stuff. For instance, like if you just had the line y equals 3x minus 2, could you make that into polar? Could you convert that to polar? This is an example of a good test question, I think. If I feel like we have time. Well, what did we say? What was our conversion? Let's see. I don't need any formulas for this. I'm just going to redraw my picture really fast. I think it's better to think about this. This is x, this is y, this is r, this is theta. And so let's see, in that picture right there, I could say, couldn't I say the sine of theta is y over r? So that means y would be equal to r sine of theta. Okay, well then I'll just replace y with r sine of theta. Again, what does it mean to convert from rectangular to polar? It means, hey, I got x's and y's. I don't want x's and y's. I want r's and thetas. All right, well, I just replaced y with r's and thetas. What about x? Well, I could write the equation cosine of theta is adjacent over hypotenuse. So I guess that means x would be equal to r cosine of theta. So again, in your book, you're going to see these conversions as though they, as though you need to be told that, as though they're somehow brilliant. No, this is SOHCAHTOA. Like you should be able to make this for yourself. So, okay, on the other side, then it'd be 3 times x, except for we just said x was equal to r cosine of theta. Done. Polar form. Rectangular form. Now, you just saw a second ago, however, and this is also true in your graphing calculator, you can't graph this unless you can solve it for r. So it's like the technology isn't sophisticated enough for me just to type that in and say, oh, look at that. It's the same exact as that line. So, maybe I can't solve this for r. Can I solve this for r? If I want to graph it and see?
Yeah, it's not too hard. You just got r's that are just regular, not squared or anything. So
yeah, you got r's there that are not squared. So couldn't I just collect the r's on the other side by subtracting them all to be together? And I don't really like that -2. I'm kind of wishing I collected it the other way, but maybe we'll change that later. And then they're only r's, so couldn't I just take the r out? So then I just solve for R. Again, I don't like negative, so I might multiply the top and the bottom by negative and write it this way instead, but that'd be the same thing. So notice, in a sense, this is a better version. This is better. Because I could actually graph this. Now, what's your opinion of lines? Well, we saw that circles were actually better in polar. Notice lines are worse. Like that's terrible. Like don't write a line that way. Like it's actually way better. It's nicer, it's simpler, it's cleaner to be y equals 3x minus 2. And yet I can go graph this and it's going to show the same exact thing. And now again, you might think, wow, that's just weird. How could you ever graph a line in polar? That just seems so strange.
I think I almost figured it out. I made a really weird graph that's kind of a parabola.
So you found one that's a parabola.
Almost. Use tan of theta.
Tangent. So you got tangent involved. Remember, tangent goes off to infinity, so you'll get some kind of weird graphs for tangent. So I would very much invite anybody that just wants to quickly show us something that they found as a graph that just thought that was kind of cool. It's worth everybody seeing it. It takes like 10 seconds to see it.
Yeah, I'll show mine.
Let's do it.
Okay.
I'm giving you the power or How come I can't do that? I have to stop sharing first. Where'd you go? There you are. I can't do this. What's wrong here?
Okay, I think I'm sharing.
Oh, okay. I think you have the power to share all the time.
So it's kind of a parabola. Goes off forever.
Yeah, so notice you got tangent of theta and cosine of theta squared. And so it kind of looks parabola-ish. It actually looks asymptotic, like parabolas go out forever.
Mm-hmm.
And this is kind of going like straight up. It's kind of asymptotic like tangent is. Tangent is actually creates asymptotes, like it won't go any further to the right. So it kind of has a parabola-ish look. It technically isn't one, but yeah, that's a wonderful graph.
It gets really weird if you change the coefficient for cosine.
That's insane. I mean, isn't that fun? That's just so cool.
It's crazy.
It's just neat. Notice you find yourself thinking, let's not do calculus with that. Like whatever calculus can do, let's not do it with that one. Isn't that fun? Yeah, and you'll notice sometimes when you get something really symmetrical, like I looked over at your window and I was like, oh, c equals 0. So that means you just took the tangent term out. So the tangent term was entirely gone. It's kind of fun.
Yep.
Anybody else find anything they want to share? I'm going to type in my line graph while I'm thinking about that. And then I will share it. I'll give you some more time at the end of class to do the same thing if you play around kind of while we're talking here. Again, one of the things that I say things like this a lot, but like the graph that Raymond just showed, for instance, like probably no human has ever seen that graph before. Isn't that just kind of a cool thought? No human has ever seen that graph. You're more than likely going to create something that no human has ever seen before. So take a look at this. Notice they really are the same. Like you can check and see that it works. I've got the green graph and the purple graph. I just turned the purple graph off and look at that. It's lined up right on top of it. So lines are not good in polar. Like if you're going to do math and you decide, maybe it'd be easier in polar. Well, it's not if it's a line. If there's a derivative and you want to find the slope, you can appreciate, wow, look, the green line, the slope is 3. I can see that. what's the slope in r equals 2 over 3 cosine of theta minus sine of theta? If it is possible to find it out, that doesn't seem like a good thing. So that's just kind of interesting. So they really are the same graph. That's kind of strange. Watch this. This is kind of fun, but how does that line actually grow? In other words, if you slowly, I'm going to do what I did before and kind of let this go from 0 to C. And then I got to say C equals 0.1 or something to get it started. Notice the line grows from 0 and it goes out there, and then it kind of goes to infinity, and then it suddenly sort of pops over and starts kind of growing the bottom side of it. Notice it seems to be done like it's kind of almost, it looks like it takes pi, like it has to have pi. So from 0 to pi and it's done. It doesn't need all 360 degrees of the angle to produce the entire line. That's kind of interesting. So it doesn't grow, it doesn't kind of get graphed in the order that you're used to thinking of a line. That's just kind of interesting to note, not important, but interesting to note. So as far as your assignment questions, this business of converting is kind of the key to things. So let's see, lines aren't all that great. What about this? This is similar to what we did before. What if I gave you the equation 4x squared plus y squared? Does anybody know what that is? If there's an x squared and a y squared, but they don't have the same coefficient. They're not both 1. Does anybody know what that is? I would guess the answer to that is no, but maybe you do.
Is that an ellipse?
Yeah, I think it's an ellipse. So it's still circle-ish in the sense that it comes back on itself. So things that come back on themselves tend to not be so bad in the kind of the world of polar. So again, if we're going to convert from rectangular to polar, we got to replace those x's. And so let's replace them. So as from above, we knew that x was equal to r cosine of theta. So I'd have 4 times r cosine of theta squared, the whole thing. And y was r sine of theta. So I'd have r sine of theta. The whole thing is squared. And that equals 36. Again, done. This is rectangular. This is polar. You're done. But maybe this could be graphed a little easier. Plus I see sine squared plus cosine squared equals 1. You know, I think maybe that will work out. So let's see, if I multiply this out, I'd have 4r squared cosine squared plus r squared sine squared. So I guess I could take r squared out of both of them. But notice this is not equal to 1 because it's not cosine squared plus sine squared. It's 4 cosine squared plus sine squared. That's not good. So it isn't going to go away. So I'm kind of stuck with that. So I guess I could solve for r at least, or if I wanted to. So r squared would be equal to 36 divided by all of that stuff. As long as I square rooted both sides. And so I'm kind of thinking, well, maybe that's not so good. Maybe that's not as good of an idea. Maybe that's a little messy. But it's not hard to convert from rectangular to polar form. I won't take the time to graph that to show that those are the same graph. And I'm a little worried because I square rooted both sides that maybe I won't get the entire parabola. Maybe the entire ellipse. Maybe I'll only get half of it. Maybe I'll get the top half or the bottom half, because remember, square root gets rid of all the negative answers that I normally would have had. And technically the equation is this, right? R squared equals that. And so maybe in that form, I'd get more answers, but I can't graph that. Like I can't, at least I can't cheat and graph it. I'd have to kind of do it by hand, which doesn't seem like a very good idea. So let's spend a few minutes going the other direction. What if I give you polar equations to graph? Like, let's convert this. What about r equals, no, those roses, wasn't this a rose? Let's throw one more thing in there. So this is like +3. So that's clearly polar because it's made of r's and thetas. So can you rewrite that as rectangular? Now remember that was a rose. Remember how crazy that was? My gut feeling is like, this isn't going to work. This is not going to work because there's no way your graphing calculator is going to produce something that looks like a rose. Remember, that's not a function. Graphing calculators or equations that are mathematically called functions can't spit out two different answers for the same x value. In other words, you got this rose thing that looks, you know, kind of like this, kind of goes spirograph on it. Whew, that's terrible. So if I said x is 3, does it make sense? 1, 2, 3. There's supposed to be 4 different answers to that problem for a crazy graph like this. Y equals x does not do well at that. My guess is this is going to break or not work well or something. But it's not hard. I mean, you just got to get rid of all the thetas and the r's. So, you know, can you get rid of them? Again, it's nice to have kind of your list of conversions in front of you. Like there's their x and y conversion. It's nice to kind of have that sitting there or earlier, but let's make it again for ourselves really quick. Just use the right triangle where this is y and this is x and this is theta and this is r to make what we need. So let's see, I want r to go away and I want x's and y. So yeah, the thing we made before was Pythagorean theorem, x squared plus y squared equals r squared. That'd be true. So that means I could replace that r with the square root of, yeah, that's what we did before, the square root of x squared plus y squared. So that's good. And then sine of theta is y over r. So that means I could replace this with y over r. And that got rid of theta, but it made an r. But then we know r is the square root of x squared plus y squared. So let's see, I think I have it now. Isn't this the equation? X squared plus y squared equals 2 plus 3 times y over r. But we said r is the square root of x squared plus y squared. So is that? And again, I could play around with this and clean it up a little bit if I wanted to. I don't know if this is cleaning it up, but if I multiplied both sides by the square root of x squared plus y squared, notice that does wonderful things on the right. What did I do wrong here, mathematicians? Mathematically, I multiplied both sides by the square root. This is not a mistake you should be making at this point, but what did I do wrong?
You got to do it to the 2.
Got to do it to the 2. What property of algebra says, what did I just screw up there? It's the same mistake people make almost every time. There's one property of algebra that people blow constantly. Anybody know what that's called? You should.
The distributive
law. You are a lawbreaker. You have broken the distributive law. So apparently those are the same graph. And I find myself thinking, wow, really? And notice, no wonder your graphing calculator can't graph this, because your graphing calculator has to be solved for y to graph that. And you can't do that. However, Desmos doesn't require that. So let's go over to Desmos and see what we get. See if those are actually the same graph, because it looks to me like it did work. I'm going to take a picture of this because I'm going to lose it when I go over to Desmos. So the polar graph We already saw this, but the polar graph, at least one version of it, the polar graph is r equals 2 plus 3 sine of theta, 2 plus 3 sine of theta. Boom. Equals. I did not hit R2. I don't know where that came from. So that's kind of fun. What do we say that was? Limicon? I don't remember. I should know that, but I don't. Rose. That was a rose. No, limicon. I hit it right. That's a limicon. So you're telling me that if we didn't make a math mistake, this other x squared equation is the same thing? If it is, I'm going to frankly be surprised. It just doesn't seems like it would not work. It just seems it would be impossible to do this to me. Well, what was that equation? X squared plus y squared on the left side. This is the easiest version I had it into. And then 2 times the square root of x squared plus y squared. Let's go in that direction. So at this point, it's just a circle. And then plus 3y. Look at that. Now look carefully. What do you notice?
It doesn't have the little loop.
Doesn't have the little hoop-de-doo, does it? So that's kind of interesting, isn't it? Actually, I didn't think we made a math mistake. So it's like it is the same graph, but somehow it doesn't seem to have the little hoop-de-hoop deal to it. So I'm kind of curious about that. I actually don't know the answer to this. I'm thinking out loud with you right now. Is there something wrong? It doesn't look like something's wrong because it's an exact match in other respects, right? But it's almost like that's as good as you can get, so to speak. So that's kind of interesting, huh? I only have one idea that I'll play with really quickly, and that is I'm going to turn this graph off. If we don't go, is there a point at which they were equal if we don't go too far, if you will? Notice the answer to that is no, because it's like right in here is where that was produced. I thought maybe it'd be produced at the end or something like that. So that didn't pan out. So yeah, that's kind of interesting. It is the same graph, but loses the little hoop-de-doo. But the point is it's not really hard to kind of go back and forth, but in a sense, this is a good problem because notice it illustrates that I guess to some extent, you can't make this graph in rectangular. I mean, you can approximate a part of it, but you can't get all of it, either for beauty or because it actually models something. That's just kind of fascinating. Now, let's see. I think I'll graph both of these and throw this in the notes just because it's kind of cool. Put it in projector mode so it's really obvious that they're different. For some reason, this needs to be green. It shows up a little better. So they're kind of the same. That's kind of fascinating. So that seems like it deserves a comment. They're almost identical. So just to get you thinking about this, we did nothing that pertained to calculus today. Did you notice that? And that is because I'm assuming at least half of you have never even heard of this before. So now at least you're introduced to the world. So we have now 2 new worlds in which to graph. Parametric, where our x and y are parameterized to each be a function of time, a separate parameter. And now polar, where we just locate ourselves on the graph using a different approach. We get there by an angle and a radius, not by an X and a Y. And it opens up this new world. And so, of course, calculus is, what are we going to do with calculus? I alluded to this a little bit, but, you know, we still might be interested in the slope of these graphs. You know, where's the slope vertical? Where's it horizontal? Where is it 1? What's the slope when the angle is 19 degrees or, you know, whatever. And so, you know, the question is, how is a derivative going to work in this world? Because we may have all the same types of questions. What we did yesterday, like the arc length, how long is this curve? You know, that spiral that goes, how long is that? What's the distance of it? That's kind of a fascinating question. I can see that we might want to know something about that. And then, of course, area. So especially for the areas like this problem that are bound automatically. Now, you may appreciate if I asked you for the red area, you wouldn't know what I meant by that. I could say, what's the green area? Then you would know what I meant. That's kind of an interesting question. Or I could say, what's that tiny little teardrop red area? But I'd have to describe that. Does that make sense? This turns out to be pretty challenging. Like this is surprising. It's really neat. But both of these, and if you're ever inclined to read ahead a little bit, one of the reasons I would encourage you to do this is because it'll, number one, help you understand that, wow, this is really difficult. Two, when you read it in a book, you'll think, I have no idea what you were talking about. Unless you're just unusually good at reading. I don't want to say just reading in general, but just reading technical things. I think you'll find if you read the 12.3 section where we're now going to do calculus with this, I think you'll find this pretty daunting. And then when I show it to you, hopefully you'll go, oh, that's all that's saying, and then maybe it won't be so bad. But both slope and area, actually I meant to not, arc length is actually pretty easy, but area, both slope and area are actually pretty surprisingly challenging. I'll just leave it at surprising right now. So you might think, oh, slope, that's easy. I'll just go dr d theta. You know, I'll have it dr d theta instead of dy dx, but it isn't that. It's way worse. It's this big old formula in order to find slope. And so anyway, we'll play with that tomorrow. Yeah, I think we're good.
Is that because theta is actually its own slope? So you have to write out the equation that theta is like a substitute for?
Yeah, that's exactly right. The problem is the slope is still dy over dx. Just because you're in this world doesn't mean you can't use dy over dx, because that's what slope is. It's rise and run. And so if I want to know the slope, which is rise and run, to try to do that with r's and thetas is strange. So I can't just say, oh, get rid of that. Let's just do r dr d theta. Well, that'll tell you how the radius changes as theta changes, but that's not a slope. Does that make sense? How is the radius getting longer as I rotate? Like for that spiral, as you rotate, what happened to the radius? Oh, it got longer. So the radius got longer when the angle got longer. That's what dr d theta will tell you, but that's not the slope. That's kind of the idea. So yeah, you're asking the right questions, Vale. All right. Anybody have any going out the door? Do we have 2 days on polar calculus? I hope. Oh, good, we do. We have Thursday and Monday, because it seems like complicated. Anybody have any cool graphs they found going out the door?
Well, talking about the last graph, I noticed that, well, I tried to multiply it out, which was a pain. I don't think I got it right all the way, but I did get a loop-de-loop when I multiplied it out. So when there's no square roots of the x's and y's.
Yeah, now think about what Ben just said. The square root of x squared plus y squared. If we have a square root, we don't want negatives, right? However, my pushback on that is if x is squared and y is squared, then it's going to be positive anyway. And so we won't have to worry about that. But the idea of, is there some way to get rid of a square root so that it doesn't have square roots? And if it doesn't have square roots, then would the loop-de-loop be in it? That very well could be possible. To get rid of the square root, you'd have to square both sides. If you squared both sides, that would be kind of a challenge. I find myself wanting to go down that road because that's a very excellent thought you're making. It's 9:20, so feel free to go if you need to go. But I usually quit somewhere between 9:20 and 9:30, so I think Ben's idea is worth following up on. So let's see if I took x squared plus y squared and subtracted 3y over to the other side, so that algebraically, when I squared both sides, it'd be easier. But unfortunately, squaring the right side is super simple because there's only one term over there. Squaring the left side, not simple at all, because I have to multiply everything times everything. I'm very worried I'm going to get this wrong. So I'm even going to write it out. Make a copy of it. So I'm going to have to take that and multiply it by itself. So let's see, what am I going to get? I'm going to get an x to the fourth term. I'm going to write this really small. And I'm going to get an x squared y squared term and another x squared y squared term for a total of 2 of them. And I'm going to get a minus 12x squared y, but I'm going to get another, aren't I? A minus 3x squared y, but I'm going to get another minus 3x squared y for a total of 6 of them. And so that takes care of all of the first x squared. Then I'm going to have a y squared times a y squared, which is a y to the fourth. And then a y squared times a minus 3y, which is minus 3y cubed. But then I'm going to have another minus 3y cubed for a total of minus 6 of them. And let's see, have I done everything times everything? Did that, but I didn't say it. I think that's it. I'm very worried that I'm not telling the truth there, though. I make a lot of mistakes because I get in too much of a hurry. So I think Ben's thought was, if I get rid of that square root and I, type that graph instead, if I haven't screwed it up, then, would that do it? I am missing one term. It's minus 3y times minus 3y plus 9y.
Yeah.
So the question is, if I graph that in Desmos instead, will that actually give me the loop-de-loop? Because now the square root's gone and we don't like square roots of negatives. My guess is no is the answer to that, because the square root of x squared plus y squared is positive anyway. However, when you square both sides, you introduce more answers. And so maybe this actually will work. So I found myself curious enough to take a picture of this and type it in over there and see.
And I guess we could just do it without multiplying it out. I did that too at first, but I guess we could just type the x squared plus y squared minus 3y squared. So
yeah,
I'll type the wrong graph.
Yeah, why didn't I think of that? Brilliant idea. So we can just say, let's let Desmos do that. So if I squared the right side, there's my picture. So on the left side, I had x squared plus y squared, but then I'm going to subtract 3y over. But I'll just say, let's just square that, and we don't have to do it. Square the other side, that'd be 4 times x squared plus y squared. Hey, look at that. So squaring both sides really did give us the rest of it. So squaring both sides, think about why that is. Why would that introduce more possibilities? Well, if you plug numbers in and on one side of the equal sign you had -3 and on the other side you had +3, you would say those aren't equal, right? But if you square both sides, suddenly they become equal. So squaring both sides actually took some answers into play that weren't in play before. It's almost like without squaring both sides, we only had one of the loops. And now we have squaring both sides, which made -3 suddenly equal to 3 and -5 suddenly equal to 5 since I squared both sides. That gave us the second loop to loop, if you will. So that's kind of fun. That's a good idea, Ben. I didn't think of that. So it's kind of weird to think that you actually can make crazy graphs like that, but they'd have to be implicit. Remember that from Calc 1, this is an implicit equation. So the question will be then tomorrow, like if that top graph 2 + 3 sine of theta, I think, okay, that looks really easy. That's a nice way to say this equation. It's small and compact and there's no squareds and all that nonsense. And notice in our equation, there's actually 4th degree terms, and there's a mixture of 4th degree terms that are X and squared terms that are Y, and like, oh, what a mess. So we know how to take the derivative of that purple graph right there by implicit differentiation. So I could actually take the derivative. Maybe that'd be a good thing to start with tomorrow now that I'm thinking about it. So I think I could find dy dx, and I said I think because maybe that isn't that simple. I think I could find dy dx, an equation for the derivative for that purple equation by implicit differentiation. The question is, could I somehow get the same answer for the top one, r = 2 + 3 sine of theta? And if so, is that going to somehow be easier? It's like a smaller equation. Unfortunately, the answer is no, it's not going to be easier. But I think we'll pick it up there tomorrow. Good idea. All right, it's 27. I should let you go.
All right.
Thank you, Doug.
Bye.
I found a weird graph. Oh, I'm the only one here.
Yeah, share it. I want to see
Well,
it.
yeah. It looks like those Japanese posters. You see, it's like there's a
Yeah.
red sun and the big
Yeah.
white rays. Then I can change this part and
Whoa. There's definitely nobody who's ever seen that graph before. Look at your crazy creation.
yeah, I had it looking like kind of an angel sort of look, but now I'm not sure how to get back to it. I mean, you can kind of see like the head and the wings and the skirt. That's kind of what I was seeing.
Yeah, for sure. Yeah, it's
Yeah.
funny how much a tiny decimal place makes, because you can actually type it. Right now it's updating by 1/10, but you can actually type 2.12 and stuff like that. Looks like a furry spider.
Yeah, yeah, an octopus.
It's terrifying. The other thing is resolution on those graphs, I think, gets really hard. In other words, I don't think the graph is what you think it is. Like, zoom in on that a little bit.
Yeah.
No, maybe it is.
Yeah, I think it's neat how it's got these crazy lines that they just don't like match up with the rest of them.
Yeah.
Like,
So true. That's hard to believe because you said 0 to 12 pi, which is basically 6 laps around the circle. So if you said if I went around 6 times, that's what I would get. What if you change that to 2 pi? If you only go 1 lap around, is it?
oh yeah, that definitely.
So see, I think it continues. In other words, in order for your graph to look as cool as it does, you need more than 1 lap. So
It's like those little plastic things that you can put into a circle frame, then you put a little plastic disc and then you use the pen.
Spirograph, yeah.
Okay.
That's kind of cool. Good find.
Yeah.
No
We'll
human
see.
ever seen that before except for me and
I
you.
know.
Isn't that amazing?
It really is. I'll see you
right.
tomorrow, Doug.
See you tomorrow.